Hey everyone, welcome back. Today we're going to dive into the theory behind numerical stability of numerical solution methods for ODEs. The last lecture, I think, the last lecture that you probably watched was a just kind of a general Python basics lecture. But the last content lecture that we went over, we talked about forward and backward Euler, and dipped our toes into the idea of numerical stability in that lecture. But in this lecture, we're going to think rigorously about stability. Okay, so it's going to be quite a mathematically themed lecture. Okay, so to consider stability rigorously, we're concerned with small perturbations, if small perturbations to the solution grow or decay. To the solution grow or decay with time, right? So, think of like any sort of numerical error, even those associated with your grid size, even or as small as flow arithmetic errors that compound and sort of explode, cause the solution to blow up, as we say. So we're going to look at the general equation dy dt is equal to f of y and t. So that's the most general first order ODE, right? And we're going to perform a Taylor series expansion of the right-hand side. Perform Taylor series expansion of the right-hand side, RHS, about or centered at y naught t naught. Okay, at some point. All right. So when we do that, we get dy dt is equal to f of yt, which we're going to approximate using Taylor series expansion centered at that point. And the way you do a Taylor series expansion in 2 dimensions is you just do the thing that you do in a single dimension, but for both dimensions. So we have a linear term in both t and y. So we have t minus t naught, that's the linear term, times df dt, the partial derivative of f with respect to t, evaluated at y naught t naught, okay, plus the linear term in y times the partial derivative of f with respect to y, evaluated at y naught t naught, and then we have t minus t naught squared times the second derivative of f with respect to t, evaluated at y naught t naught, plus this, of course, should be divided by 2, so this would be 1/2, plus 1/2 y minus y naught squared, partial derivative of f with respect to y squared, and y naught t naught. And then we get some third order terms in both x and y. So we have y minus y naught cubed, and then other error terms that are t minus t naught cubed. Okay? So, here's what we're going to do. We're going to throw out all the terms of second order or higher. Okay, and this is called linearization. Okay, so to proceed, we throw out all second order and higher terms. Yielding a linearization of our original ODE. Yielding a linearization of our original ODE, which has the following form, where dy dt is approximately equal to lambda y plus alpha 1 plus alpha 2 times t. Okay, what these constants are is, if you look above, right, we have the only term in front of the y here is this constant df dy. So lambda y is equal to the partial derivative of f with respect to y, evaluated at y naught comma t naught. Okay, and then the constant term has like the y naught t naught terms. So that's talking about everything attached to like this y naught here and this t naught. Remember, everything in the second order or higher we just threw out, right? And then we have one more linear term in t that we have, and we can see that that's going to be, that alpha 2 is going to be equal to df dt evaluated at y naught t naught. Okay, so now remember, this is just a representation of the first order behavior of our ODE. Okay, so the solution to this differential equation is not going to be exactly correct, but it's going to be correct to first order. Okay, it's like the most dominant behavior is going to be captured here. So then let's sort of think about what this solution is for a second. What this equation is. So let's categorize this equation. What is this equation? Well, we know that it's non-homogeneous. It's second order. First order. It's linear. Obviously, it's first order. It's linear, and it has constant coefficients. And like, as I said, it's first order. Okay. It has a homogeneous solution. Which we can easily see is going to be yh is equal to c times e to the lambda t, right? So you can see that if you drop the non-homogeneous part, you get that. And then we know from the method of undetermined coefficients that the particular solution is going to be of the following form, where you have yp is equal to some constant times t plus b, right? And so then the question, you look at both of these, so you know that the general solution to this linearized equation is going to be a linear combination of those two solutions. And the question becomes, which is most interesting when it comes to stability? Most interesting for stability. And remember, when we're talking about stability, we're talking about things blowing up in an uncontrolled way. Now, things can grow linearly with time, but an exponential growth is a lot more concerning, right? So we're actually more concerned about the homogeneous solution. What we've essentially shown here is that for the first order behavior of our solution, which is represented by this linearized equation, the component of that equation that leads to that's going to lead to the unstable, uncontrollable growth and behavior is captured by the lambda y term. And so therefore the model problem, and this is another like term to remember what we mean by model problem. So the model problem that we analyze for stability is dy dt is equal to lambda y, where we know that the solution y of t is going to be y naught times e to the lambda t, right? So, just to put it in words, this is the most stability relevant component of the linearized version of a general first order ODE. So it is broadly applicable, right? So let's talk about what lambda is, okay? So another thing to keep in mind is that lambda has a real and imaginary part in general. So lambda r plus I lambda I. Okay, so if lambda I is not 0, the solution is oscillatory. And that just has to do with the fact that e to the I theta is equal to cosine theta plus I sine theta, right? But lambda r is the most important component. This is the critical component. Is the critical component. If lambda r is greater than 0, then the solution grows exponentially. Okay, so we know how exponents behave. We're familiar with this. Okay. Let's see. Do I want to do this? Yeah, I should probably introduce this idea really quickly, and then we'll go back and take a step back. So let's say that we're going to make one little aside here and note, and we're actually going to return to this when we talk about higher order equations. But I do want to say that this linearization concept extends to second order equations. Okay, so let's look at, consider the following. So consider y double prime is equal to omega squared, plus omega squared y is equal to 0. We can rewrite this as a set of first order equations, right, where we define y2 is equal to y1 prime, and y2 prime is equal to, sorry, I should do y2 prime is equal to y1 prime is equal to y2, and y2 prime is equal to minus omega squared y1. Okay, so we basically just took this y and we replaced it with y1, and then we defined y2 as y1 prime. What that looks like in matrix form is that you have y1, y2 prime is equal to this matrix, which is 0, 1, minus omega squared 0, times the dependent variable vector y1, y2, unprimed. Okay. So, and this is where your linear algebra knowledge needs to come in. Okay. So we're going to call this thing A, and this is like your system matrix for your set of differential equations. And I'll also say that we're going to cover this again in a bit, but I just wanted to, while we're here talking about linearization, make this note, and then when we go back to higher order ODEs, we'll make this point in more detail. So what you would want to do is what's called diagonalize A. Okay, and what I mean by that is that we want to decompose, that is, decompose it as A is equal to S capital lambda S inverse, okay, where lambda has the eigenvalues on the diagonal, lambda 1, 0, 0, lambda 2, so it's the diagonal matrix with the eigenvalues on the diagonal, and S is a coordinate transform. Composed of the eigenvectors of A. Now this is actually stuff that you should have learned in your Math 341, your linear algebra course. I understand it might be rusty, and this was probably the topic of that might have been the most complicated, is diagonalization, eigenvectors, and eigenvalues. But we'll return to this, and you'll get a lot of practice with this. So don't worry if you're getting bewildered by this. But in the end, you have a new system, which you can just say z prime is equal to lambda, capital lambda times z, where z is equal to S inverse times y. Okay, and y is this vector here. Okay, so I'll put vector signs about this to make it more clear. Okay, and then for this problem, you get z1 prime is equal to I omega z1, and z2 prime is equal to negative I omega z2, which are both in model problem form. Where you have, y prime is equal to lambda y, right? Okay. I realize that might be kind of like what you might be thinking, what is going on here? But don't be overwhelmed. This is just get this down on paper, and then it will help when you are solving higher order systems to go back and think about this, and when you're asked questions about the stability of those systems. Okay, so but the whole point is that this is the general process by which you convert a a higher order system, which is composed of a coupled set of first order equations, this is how you convert that to the model problem form, and shows that the eigenvalues in particular take the role of lambda. Okay. All right, so let's take a step back for a moment here too. Okay, so since we just kind of strayed into a more complicated region there. So far, we started with a general first order ODE. Okay, which is just y prime is equal to f of y and t. Okay, started there. Then we used Taylor series to linearize this equation. Okay, what's happening there? Linearize this equation by dropping second order and higher terms. Order and higher terms. That left us with y prime is equal to lambda y plus alpha 1t plus alpha naught, whatever. I don't think those are the exact same subscripts I used before, but we can just not worry about those. We note that the exponential part is where the dominant growth component of the solution will be located. Okay, so exponential part was noted to be most relevant to stability. So we choose to analyze y prime is equal to lambda y, where lambda is equal to df dy at some point. Okay, and that's what's important, where this note right here is that this is only true at a single point in the domain. Like in general, lambda evolves with time. Okay, so what we're about to jump into is a way of coming up with stability criteria, and it could be that the lambda based on your initial condition is one thing, and then later in time it is a different value, which could lead to unstable behavior. So one thing to keep in mind. Okay, so if lambda r, the real part of lambda, is less than 0, then our model problem solution does not blow up. Okay? And remember, the solution to the model problem is describing the first order behavior of the solution to the general ODE. Okay? So any sort of unstable behavior is going to be captured within that. All right? So cool. So that's where we leave ourselves. Okay? So this is the background for stability theory. It really just did these sort of four observations in a row. Okay, that's how you develop it. Now let's go ahead and apply forward Euler to the model problem. Applied to model problem. Whoops. Okay, so let's go ahead and do that. We have the general forward Euler scheme, which is that Fn plus 1 plus, let's say that our overall equation that we're trying to solve is the following. Is y prime is equal to lambda y. Okay, that's the model problem. We showed that or not showed, but we learned last time that the forward Euler scheme is that yn plus 1 is equal to yn, or y at the previous time step, plus your grid size times lambda yn. Okay, so whatever the right-hand side of the differential equation is, evaluated at the previous time step, so it'd be yn. Okay, so if we go ahead and do that, we can expand lambda into its real and imaginary parts. Yn plus h times lambda r plus I lambda I times yn. Okay, and then we can see that we're getting a nice amplification factor here. 1 plus h lambda r plus I h lambda I times yn. Okay, and this whole thing here is sigma. So remember, the amplification factor is the number by which you can multiply the dependent variable at the previous time step to get the next time step value. Okay, so for stability, we need the magnitude of sigma, our amplification factor, to be less than or equal to 1, right? So what we're going to do is assume the real solution doesn't blow up. Actually blow up. So like the proper behavior would be that the solution would not exponentially grow with time. Okay, so that means that we're assuming that lambda r is less than or equal to 0. Okay, we're going to make that assumption up front, and then we get this equation, right, where the absolute value, or the magnitude of sigma, is equal to the square root of 1 plus h lambda r quantity squared plus h squared lambda I squared. And we need that thing to be less than or equal to 1. Okay, so that this is our general stability criterion. Okay, and the way we visualize this is with a stability diagram. We visualize this with a stability diagram. Okay, and so what is a stability diagram? Okay, so what we do is we draw the complex plane. And we normalize it by h. So we do h lambda r and plot h lambda I. Okay. And then we have our grid points here. So let's think about this general equation that we have here. How can we represent this? Well, the edge, okay, there's a set of points for which the magnitude of sigma is identically 1, right? And that would be represented by 1 plus h lambda r squared plus h lambda I squared is equal to 1, right? Because we can square both sides of this equation. And that equation, if we're looking at h lambda r and h lambda I as the x and y variables in this plot here, that's going to define a circle in that xy plane, right? And moreover, it'll be a circle centered at -1, 0, based on what the arguments of these squared quantities are. And so we get this disk that looks like this. In fact, let me, I think there's a way to make a nice, yeah, there we go. Whoops. Make sure this is nice and centered here. Okay. Okay. All right, nice. So that's the set of points that this equivalence is true, but remember it's actually a less than or equal to sign. So in that case, everything on the inside of the circle has a stable solution. So lambda living, or should say h lambda living in here, yield a stable solution, or a solution with an amplification factor that is less than or equal to 1. Okay. Now, there's something important to note here. So, note here, a purely oscillatory solution is actually unconditionally unstable for forward Euler. So a purely oscillatory solution is actually unconditionally unstable. For forward Euler. And the reason why that is because if lambda happens to be purely imaginary, which is what leads to a purely oscillatory solution, it's going to live on this axis here. And there is no point, except for with lambda equal to 0, which is meaningless, for which you are going to have stability in that case. So when you're using forward Euler, explicit Euler, if your solution is purely oscillatory, or even if it has a very strong oscillatory component or behavior, it's almost certainly going to give you a non-physical result. Okay. So that's something to keep in mind. Okay, so now let's look at what implicit Euler looks like, right, using this analysis. Now, implicit Euler. So implicit Euler has the different behavior where yn plus 1 is yn plus h lambda r plus I lambda I times yn plus 1, right? And what this gives us is the following amplification factor where we have 1 divided by 1 minus h times lambda r plus I lambda I times yn. So this is now our new application factor. Okay, and then we go ahead and write down our stability criterion, which is that the complex magnitude of sigma has got to be less than or equal to 1. This is 1 over the magnitude of 1 minus h times lambda r plus I lambda I, which is equal to 1 over the square root of 1 minus lambda r h squared plus lambda I h squared. That has to be less than or equal to 1. Okay, and then we can rearrange this by multiplying both sides by that denominator and then squaring the result. And we can see that the stability criterion becomes 1 must be less than or equal to the quantity 1 minus h lambda r squared plus h squared lambda I squared. Okay, so let's go ahead and draw this. So in general, when you're drawing these, you should just look at the line of equivalence first. Of course, makes it more straightforward. Let me make that a little bit more clean. We're plotting on the complex plane, so we'll look at h lambda r versus h lambda I. Okay, and then we can see that the border here is going to be centered at 1, 0 because the sign changed inside of this argument. And so we go ahead and make our circle. Shouldn't have done it there, I should do it right here. Okay, just make sure that this is nice and clean here. I should probably just bring in that hash mark. Okay, and sorry, just cleaning up the drawing here. Okay, and then look at the way this inequality faces here. Okay, it's saying that it's not saying that everything is less than 1. It's saying that it's in effect it's saying everything outside of the circle is stable. Okay, and so we can go ahead and shade the entire domain outside of this disk, and we can see that implicit Euler is stable for all non-growing solutions. Where lambda r is less than or equal to 0. Okay, and therefore it's unconditionally stable. Okay. So yeah, so that's that. Now you've seen sort of implicit and explicit Euler. Let's before we let me think here. Will you ever see an example of this? Should I? Oh, I can do it on the Runge Kutta. Okay, let's talk briefly about the trapezoidal method. So we talked about the trapezoidal method as a integration method, but of course, when you're solving a first order ODE, it's really just an exercise in integrating, right? You're integrating you're integrating the derivative. And so, going back to our general equation where we have y prime is equal to f of y in t, we can express the solution as y of t is equal to yn plus the integral from tn to t of f of y of t and t dt. So this is going to be a t prime. We're going to make that the integration variable, which leads to, yn plus 1 is equal to yn plus the integral from tn to tn plus 1 of f of y of t prime and t prime dt prime. Okay, and then we can approximate this however we like. But here we'll use the trapezoidal rule. Okay, and then what you end up with is the following, which is yn plus 1 is equal to yn plus h over 2 times f evaluated at yn plus 1 and tn plus 1 plus f of yn into tn. All right, and then we know that the local error for this is third order because we covered that in our integration lecture. Okay, so this is the trapezoidal rule for solving an ODE. Okay, you're just using the trapezoidal integration method. So let's go ahead and apply this method to the model problem to look at what the stability of this method would be. So if we sub that in, we get yn plus 1 minus yn on the left-hand side is equal to h over 2 times lambda yn plus 1 plus lambda yn. And we can rearrange that to be yn plus 1 is equal to 1 plus h lambda over 2 divided by 1 minus h lambda over 2 times yn. And so our amplification factor is this more complicated thing, right? And if we look at what the amplitude of the complex amplitude of the amplification factor is, you get the following, where you have 1 plus lambda r h over 2 squared plus lambda I squared h squared over 2 divided by 1 minus lambda r h over 2 squared plus lambda I squared h squared over 2. Oh, over 4 rather. These two should both be over 4 because 2 squared is 4. And then the question is this stable? and it's actually unconditionally stable. Because for non-growing solutions, for lambda r less than or equal to 0, the denominator is strictly smaller than the numerator. Right, so this or strictly larger, sorry, excuse me. The denominator is strictly larger than the numerator, which will always give you a complex magnitude that is less than 1. Okay, and then another thing to note here is that consider the purely oscillatory case. Which is that lambda r is equal to 0, right? In that case, the magnitude of sigma goes to 1. And so you actually accumulate no amplitude error in undamped oscillating systems. And this is another sort of point to take into account. So we've been talking a lot about stability, right? We want our numerical solution to just not blow up. But there's also the error that you're accumulating, right? And we don't have enough time in this course to really delve into this, but there's two types of error that you can accumulate, which are amplitude and phase error. Phase error has to do with shifting forward and backward in time, okay? And then amplitude error has to do with the amplitude. So for the implicit Euler, you could have a solution that is purely oscillatory, and you're still going to, so looking at what the amplitude of sigma is here for implicit Euler, if your solution is purely oscillatory, that is, it has lambda r equal to 0, or the real part of lambda equal to 0, you're still going to have an amplification factor whose magnitude is less than 1. So actually over time, your oscillations are getting damped, even though that's not a real part of the solution. Okay? Does that make sense? So you're actually picking up some amplitude error with implicit Euler, and that has to do with the lower order of accuracy of implicit Euler. But it also has to do with just the dynamics of how implicit Euler works numerically. Whereas with the trapezoidal rule, you actually have no amplitude error in undamped oscillating systems, and that's a good reason to use this method for physical systems where you expect there to be undamped or at least oscillations with very little damping. Okay, and so the stability diagram looks like this, where the entire left-hand plane for lambda r less than 0 is all stable, but so it's an unconditionally stable system, but also right on that axis, that lambda r equals 0 axis, for all of that you have sigma is equal to 1. So that, for that reason, trapezoidal is a preferred method if you know that the dynamics of your system are highly oscillatory. Okay, one more topic here, and we actually touched on Runge Kutta in the numerical lecture. And we're going to cover it here, a higher order version of it, which is the most popular time advancement scheme. And if you ever use sort of an automated tool for solving a differential equation that takes default arguments, the odds are it's going to deploy a fourth order Runge Kutta, or what is often referred to as RK4. Okay, this is a very very popular method, and it's explicit as well. So basically, to sort of to summarize what Runge Kutta methods do, is they introduce intermediate points between grid points. So in this case, it would be like Tn and Tn plus 1, and evaluates f at those points. Which, remember, f is the right-hand side of the equation at those points. Okay, so you get a good accuracy payoff, but most importantly, you get a good stability payoff as well. So what RK4 looks like is the following. This is the let's say the algorithm definition. So we have yn plus 1 is equal to yn plus k1 over 6 plus 1/3 times k2 plus k3 plus k4 over 6. Okay, and then k1 is defined as h times f of yn tn. Okay, and then k2 is h times y of evaluated at yn plus 1/2 k1, and then at tn plus h over 2. Okay, and then k3 is equal to h times f evaluated at yn plus 1/2 k2, tn plus h over 2, and k4 is equal to h times f evaluated at yn plus k3 and tn plus h. Okay, and then this is very easy to program because it's explicit. But it's costly because of all the function evaluations. Okay, so that's where you're paying for the extra accuracy and instability. Now the stability diagram for this is very complicated to derive. You can derive this method using Taylor series, and I think it's done in the text by Moyne that I've given to you. But the stability diagram for Runge Kutta 4 ends up looking like this. Okay, it has this general shape. It goes up like this, and then it has a lobe, kind of comes around here, and then that thing is mirrored across the x-axis. So let's see if I can draw something that looks roughly mirrored. That's pretty close. Okay, and then this value up here on the y-axis where it's crossing is 2.83, and then the value at which it's crossing the x-axis is minus 2.79, and remember we're plotting h times lambda here, h times lambda r and h times lambda I is equal to those values. Okay, and it's stable for the interior of that shape. So an important thing is that you have an explicit method here, but it is conditionally stable for purely imaginary lambda. Okay, so if you have an oscillatory solution, this can still be stable. Now, how do you use these stability diagrams? Okay, so I really should, in the lecture, should have tried to explain this when we looked at explicit Euler, but I think it's easier to see with this diagram because it includes sort of a real and imaginary part. But what you're going to do when you do this, so if you're presented with a general differential equation, dy dt is equal to f of y in t, the first thing you're going to do is you're going to calculate lambda, calc lambda, which is going to be equal to df dy, and then you're going to evaluate it at some point that you know exists. It might be the initial condition, so usually it is. It's like you're given the value of y at t0. Okay, so then you evaluate that, and you're going to get some value. It's going to be like a plus I times b, right? And let's say for the sake of argument that b is equal to 0 for now. So example, b is equal to 0 and a is equal to 20. Okay, so then you know that lambda is equal to 20, right? Well, you have a purely imaginary, we'll say a is equal to minus 20. Okay, and so you know that lambda is equal to minus 20. Okay, well, let's look at the stability diagram, right? We're dealing with a purely purely real lambda. That's minus 20. So we're looking at the points on this line here that I'm drawing over in red. Okay, and we can see from that we know that h times lambda r, okay, has got to be it's got to be less than or equal to 0. So that's this point here, and it's got to be greater than, and it's got to be greater than minus 2.79. Okay, and we just found that lambda r is minus 20. And so what we can do is we can say we know that minus 20 times h has to be greater than or equal to minus 2.79. Okay, we divide both sides by negative 20, then we see that h has to be less than or equal to 2.79 over 20. And that is our stability criterion. Okay? As a different example, say you have b is equal to 4 and a is equal to 0. Well, in that case, you're looking at this axis here that I'm lining up in blue. Okay? And you can see that in that case, you need h times lambda to lie in between minus 2.83 and h times lambda I and 2.83. Okay, lambda I happens to be positive here, and h is always a positive number. So that one doesn't matter. The left-hand side doesn't matter. And then you just get that you have 4 times h has to be less than or equal to 2.83, and h has to be less than or equal to 2.83. Okay? And then, it goes on and on. You could have the case where both are non-zero, where you have b equals 2 and a equals 10. Well, in that case, you're going to be, somewhere out here. Okay, and all you need to do is you need to use h to scale yourself back into the region of stability. Okay, kind of along this line that's represented by, 2 and 10. Okay, hopefully that makes sense. That's something that I didn't actually really explain on the first time through, and it caused some people a little bit of grief on the homework. So hopefully that makes this a little bit clearer how you use these stability diagrams. If you have any questions about this, please come to office hours or go ahead and reach out. But otherwise, that's the end of this lecture. And then in the next lecture, we're going to talk about higher order initial value problems. And that's where we'll kind of go back to doing that stability analysis of systems of equations, okay, and linearizing higher order systems of equations. Okay, all right, so that's it for this one. Thanks for listening, and I'll see you next time.